Heating and cooling. Touch something hot and your senses immediately tell you to pull your hand away. Hotness is about the amount of heat energy an object has. A spark from a firework may be very hot, but it will not hurt very much because it does not contain much heat energy. However, even though a cup of tea may not be very hot, it can still burn the tongue because it contains a lot of heat energy. These sparks do not have much heat energy. You can burn yourself with this tea even though it is not very hot. Temperature and heat. Heat and temperature are not the same. Temperature is a measure of how hot or cold something is. Heat is the transfer of energy from a higher temperature object to a lower temperature object. Temperature is a measure of how hot or cold something is. It is measured in degrees Celsius. Degree Celsius. Temperature is measured with a thermometer. Heat is the transfer of energy from a higher temperature object to a lower temperature object. It is measured in joules, J, or kilojoules, kJ. You already know that solids, liquids, and gases are made up of tiny particles. These particles are moving about all the time. The more energy the particles have, the more they move about. The opposite is also true. As they lose energy, they move about less. This change in energy is what heat is. As a solid cools, heat energy is removed. The particles will move more and more slowly until they stop moving altogether. The temperature at which the particles stop moving is called absolute zero. Absolute zero is the temperature at which a material has no heat energy. This temperature. For scientific work it is convenient to use a temperature scale starting at absolute zero. This temperature scale is called the Kelvin scale. It starts at absolute zero and has degrees which are the same size as degrees on the Celsius scale. Heat is about moving particles. You have learnt that everything is made of particles called atoms and molecules. They are constantly on the move, either vibrating or moving freely. It is the motion of particles that creates form of energy called heat. The movement of particles is affected by temperature. The higher the temperature, the faster particles move. This is known as the kinetic theory. Solids do not contain a lot of heat energy. Each particle vibrates around its fixed place in the framework. Example, ice. Liquids have more heat energy than solids. Particles are able to move around by rolling over each other. Example, water. Gases have most heat energy. Particles move very quickly and are free to move in any direction. Example, steam. The kinetic theory can help explain how substances behave. The loss or gaining of heat can change the state of matter. Melting. If a solid is warmed, its particles move faster until some break free and become part of a liquid. Evaporation. If heat is applied to a liquid, the particles move faster still. At the surface the faster particles break free to form a gas above it. Condensing. When heat energy is removed from a gas, its temperature falls. The gas particles slow down and move closer together. Eventually they will come close enough to form a liquid. Freezing. As a liquid cools, the particles slow down. Eventually they will start to form a framework which is like that of a solid. Mass is conserved in these changes of state. Only the behavior of the particles changes. The actual particles remain the same all the time. Therefore the total mass of the substance never changes. Water is turning to steam in this kettle because heat is making its particles move faster. Did you know? The word kinetic comes from the Greek word kinesis, which means motion, transfer of heat. Heat can be transferred from one place to another in three ways. Conduction. Heat can travel through solids. You will know. Heat, thermal. Heat can travel through solids. You will know this if you have ever tried stirring hot soup in a saucepan with a metal spoon. Heat, thermal, energy flows quickly from the soup through the spoon to your fingers, which soon begin to get hot. The movement of heat through a solid such as a metal is called conduction. The metal spoon conducts heat from the hot soup to your hand. Metals are the best conductors of heat because heat can travel through them easily. Cooking utensils are made of metal so that the heat from the cooker can get to the food quickly. Non-metal solids such as glass and plastics tend to be poor conductors, and so do most liquids. Materials such as fur. Poor conductors of heat are called insulators. Air is a very good insulator. Materials such as fur Feathers, wool, plastic foam, and glass or mineral wool are good insulators because they contain pockets of trapped air. Conduction and the kinetic theory. If one end of a metal bar is heated, the particles gain thermal energy and vibrate faster. This causes the particles next to them to vibrate faster as well. Bit by bit the increased vibration of particles is passed along the bar until the whole bar is hot. Heat has been conducted along the bar. Did you know, copper is the best conductor of heat? It conducts heat 10 times better than iron. When heat energy travels by conduction, the energy is passed from one atom, or molecule, to the next. It is the heat that flows, not the heated atoms. Convection. Liquids and gases may be poor conductors of heat, but they can carry heat because their particles are free to move around. Convection cannot happen in solids because the particles are held in a framework and cannot move around as they do in liquids and gases. This happens when water is boiled in an electric kettle. The heating element in the kettle only warms the water touching it. Warm water is less dense than cold water, so the warm water rises. This is called convection. Cold water replaces the rising warm water, and this, in turn, also becomes warm and rises. A continuous circulating stream is set up in the kettle. This is called a convection current. Heat energy must travel through gases because a room can be warmed by a heater. Warm air is less dense than cold air, so the warm air above the heater rises and is replaced by denser cold air. As in the water in the kettle, a convection current is set up and air circulates around the room. During the day, land is heated by the sun much more quickly than the sea. This sets up a convection current, so air moves in from the sea. When damp air from over the sea rises, it cools to form clouds. Radiation. When we cook food under a grill, heat must travel downwards from the heating element in the grill to the food. This heat cannot be carried by convection because convection carries hot air upwards. The heat cannot be conducted to the food because air is a bad conductor of heat. So, there must be another way of moving heat to the food. This is by radiation. The heat travels as tiny electromagnetic waves called infrared waves. The hotter an object is, the more infrared radiation it emits. No particles are involved. Unlike in the processes of conduction and convection, so radiation can even work through the vacuum of space. This is why we can still feel the heat of the sun, although it is heat, and light from the sun reaches Earth as electromagnetic waves. Emitters and absorbers. Some surfaces are better at emitting, giving off, thermal radiation than others. Good emitters of radiation are also good absorbers. White or silvery surfaces are poor absorbers because they reflect most of the radiation. That is why in hot, sunny countries houses are often painted white to keep them cool inside. Did you know? Firefighters enter smoke-filled rooms by crawling on the floor. This is because smoke rises by convection up to the ceiling. Comparing emitters. 2 metal cans are filled with the same amount of water at the same temperature. Can A has a dark surface, can B has a shiny surface. The graph shows that the water in can A cools more quickly than that in can B. Clearly, a dark surface is a better emitter of thermal radiation than a shiny surface. Comparing absorbers. 2 metal plates, one shiny and one dark, have thermometers attached to their backs. The plates are fixed at the same distance from a radiant heater. The graph shows that the dark surface absorbs heat more quickly than the shiny one. Clearly, dark surfaces are better absorbers of thermal radiation than shiny surfaces. The vacuum flask. A vacuum or thermos flask can keep drinks hot or cold for hours. The flask has a number of features which reduce the rate at which heat flows in or out of it. The stopper reduces heat loss by convection and conduction. The space between the walls has the air removed. Vacuum, so heat loss by convection and conduction is reduced. The silver lining of the walls reduces heat loss by radiation. Did you know? The vacuum flask was designed and invented by Scottish scientist Sir James Dewar in 1892. The Thermos Company was the first to mass-produce vacuum flasks for everyday use. More about changing state. Earlier in this chapter you read about the kinetic theory for the way particles behave during melting, evaporation, and condensing. Let us see what happens when some crushed ice is heated. The ice is gently warmed until it melts. The heat is then turned up until the water begins to boil. The temperature is taken every 30 seconds from start to finish. The water in this puddle will soon disappear. Heat from the surroundings will make the water evaporate. The graph shows the results of the investigation. What does the graph show? Stage 1. The heat energy is raising the temperature of the ice up to 0 degrees Celsius, melting point. Stage 2. Here there is very little temperature rise. The heat energy is being used to allow water molecules to break away from their fixed positions in the ice. The solid is turning to a liquid. Stage 3. The heat energy is raising the temperature of the water up to 100 degrees Celsius, boiling point. Stage 4. Here there is no temperature rise. The heat energy is being used to allow water molecules to break free completely. The liquid is changing to a gas. Did you know, not all substances melt at the same temperature? Solol, phenyl salicylate, is a sweet-smelling chemical used in the making of soap. Solid solol melts at around 41 degrees Celsius.